Okay, in this video, we're going to look at the most important concept in engineering economics and financing, the time value of money. Now, to give you a very textbook definition of this concept, you will see this quotation in many textbooks like Turton or most of the engineering economics textbooks, even finance and business textbooks. The quotation goes as money now is worth more than money tomorrow. That is the essence, the most simplified explanation of this entire concept in just one sentence. Basically, let's dig deeper a little bit and see what it means for us in everyday lives and in context of chemical engineering plants or any engineering projects for that matter. Let's say I give you $100. Let's say, let me write that here. I give you $100 cash today versus now, now, okay, so far $100 in cash today versus the same cash amount. $100 today versus the same cash amount 15 years later. Even though they are the same cash amount, you have a $100 bill here, you have a $100 bill here. But are they the same value? Think about it for a second, just using common sense. Of course, the value of money today is going to be higher than the value of money tomorrow. And what's the reasoning behind that? Is it we're talking about a reasoning other than the mere fact that inflation is going to happen and people are going to lose their purchasing power, etc. We're just concerned with the simple fact that money, if I give you money today, let's say I get these $100, they get deposited in my account. Okay, now I have I have so many options how I spend this money. I can just go buy myself a PS4. I can just like save up for a PS5. I can like spend some money on the latest. I can pre-order Call of Duty Black Ops Cold War, the collector's edition, just like throw it away, or I can save it, or this is what like economists and finance experts say that like um, the wiser people, the people, they're gonna actually invest their money. So let's say you take $100 and invest it in a business. In a small scale business, it could be well, let's not even talk about a business venture right now. Let's talk about something so simple like a savings account that gives you that compounds at 15% annually, let's say. This means that each year that $100, let's say you deposit it at year, the current year being year zero, you deposited $100. The next year, in year one, it's gonna be 100 times 1.15. The next year, it's gonna be 100 times 1.15 times 1.15, and so on until let's say year 15. 100 plus 0.15 raised to power 15. Okay. So now compare this. You didn't start a business. You didn't do any significant investment. You just put your money in a savings account that compounds 15% annually. This money, the cash, the $100 cash that you got today, after 15 years, fast forward 15 years, this cash has now been converted into 100 times 1.15 raised to power 15. Let's calculate how much that is real quick. Okay, so we have 100 times 1.15 raised to power. Let's see, how do I do this? Hmm, hold on. Just a little bit of trial and error here. Bear with me. 15 raised to power, there we go, 15. $813.7. See, a small amount of $100 has been converted to 813.7 cash amount after 15 years, compared to just getting a $100 cash bill after 15 years. We have cemented the fact that money generates more money, which is which makes it preferable to get money now so you can make investments today and get a positive rate of return in future. All right. Now, obviously, this 15% compound is an exaggeration. You'll be very lucky. And let me know if you find a bank that lets you compound your savings at that rate. But this rate of return, like the rate of return in most chemical projects, let's say the minimum rate of return that investors and project managers look for is between the range 10 point 10% to 20 to 25%. It depends. Which means that like as long as you're getting a 15, 10, 20% rate of return, the chemical plant is a good investment. We're gonna dive deeper into rate of return and the mathematics behind it. So far, uh, one thing that we need to really grasp before ending this video is that all the calculations for time value are going to be based on compound interest. And to understand that, let's give you an example. A very similar example to the one that I just did earlier. Okay, let's say David gets a 200 $2,500 bonus in 2012. He puts the amount in a savings account that compounds 2.5% annually. Okay, how much money will he be able to withdraw in, let's say, 2020. Okay, so the formula that we're going to be using, the one formula that I want you to really have a good understanding and grasp of, is that the future amount, let's just write the formula first. F equals P times 1 plus I raised to power n. F is the future amount, P is the present amount, I being your interest rate, and n being the compounding period, which in our case is it's compounding each year. So between 2012 to 2020, we're going to have 8 years. Okay. So, and this entire statement can be represented on a cash flow diagram in the following manner. So we're going to take 2012 as year 0, and we're going to 2020, so that's going to be our year 8, 6, 7, and 8. Okay, so the money is deposited at the initial period, the year 0 being 2012, obviously this being 2020, and we're looking for the amount that we will be able to withdraw after 8 years. Okay, we know how much amount we're depositing, we know our interest rate, 2.5%, and n is going to be 2020 minus 2012, that's 8 years. So our value, the amount that we'll be able to withdraw in 2020, is going to be 2500, the present value, plus 0.025 raised to power 2020 minus 2012, which is basically 8. Okay, and this turns out to be, let's see, all right, 2500 times, hold on, oops, 2500 times 1 plus 0.025, that's 2.5%, all of that raised to the power 8. Give me 1 second, I think, oh no, sorry, yeah, let me just rewrite that. 2500 multiplied by 1 plus 0.025, that raised to power 8. There we go. That looks much more believable. So in 2020, he'll be able to withdraw around $3,047. All right. So in the future videos, we're gonna look at a couple of examples that really enforce the problem solving techniques associated with time value of money. We're gonna look at different loan problems. We're gonna look at converting present present cash flows to future cash flows, and we're gonna look at different forms of investments that you'll see, calculating annuities and gradient payments. We're gonna look all into all of that in the coming videos. But at the heart of all of this, if there's like one formula, one concept that I want you to really, really understand, this right here. Because all of the other formulas all are gonna be based on this right here. This basically, in essence, is the single formula that you need to have a good handle of in order to understand time value of money. We're also going to be using a lot of Excel in the coming problems, so it will be helpful if you have a working knowledge of Excel. But the problems, you won't be at a disadvantage if you haven't been using Excel for a while. So yeah, stay tuned.